Hey, we have here today another integral on the board. This one's from the MIT Integration Bee 2022 finals problem number 3. We have the integral from 0 to 2 pi of this whole big expression with a bunch of sines and cosines in it. To start with, the first thing I noticed really was these two sine expressions over here. And what jumps out is these are really close to being in the correct form for the Dirichlet kernel. Anyway, the thing I noticed comparing each of these to our formula over here, like in this first one, our angle here is 50x, where we need our angle to be x over 2. Well, I can take care of that pretty easily by making a substitution. So I'll substitute, we'll call 50x equal to t over 2, and then I can just get a value for t as 100x, or we can solve for x as t over 100. So then taking just this first expression here, sine 50x becomes sine of t over 2. And then in the numerator, if we just divide 50x into that 10,050, this becomes sine of 201 over 2t. But then I can break this up exactly in this form. So what I need to do here is if I take a half out of this in the numerator, we can split off a half or a t over 2. That's going to leave me with 200 over 2, but 200 over 2 is just 100. So we're going to have 100t here over sine of t over 2. So then matching up with this formula here, our n value is going to be just 100. So now we'll use this formula and we'll have 1 plus 2. We're going to have the sum from 1 to n, which is 100. And this is going to be cosine of kx. And next what I'm going to do is the exact same thing for this sine of 51x. We'll just substitute for 51x. I'm not substituting into the integral. This is just like an algebra substitution, but I'll use another variable anyway. We'll set 51x equal to y over 2. And then y is going to be 102x, x is going to be y over 102. So then rearranging this, now we're going to have this sine of y over 2 in the denominator. And then when you do the numerator, it ends up exactly the same way. This is going to be, because when you divide 51 into 10251, it works out the same way. You're going to have 201 over 2y, and we can rearrange it this way and write it as sine 100y plus y over 2. And so using the formula again, so we'll use this and we'll write it as 1 plus the sum from, we'll use a different index, we'll say from j equals 1 to 100, and this is going to be cosine of jx now. And so we can just take this piece and put it back in our integral for this one right here. Okay, so now at this point you can see we've eliminated all sine functions from this thing and we just have cosines all the way through it. And what I want to do now is I want to just multiply this out. So let's just see what happens when we distribute out this part. Okay, so now you can see our integral just got longer and we've got a bunch of sums over here. This last piece is a little bit scary. So I could multiply this in right now, but I think I'm going to skip that for the moment just because it's going to make my expression even longer. But we can kind of see what's going to happen when we multiply in our cosines. So we're going to end up with 4 different integrals because we have 4 terms here. So what I'm going to do is kind of take these one at a time, and I'll just start with this first one. Multiplying cosine 22x times 1 is just going to give me the integral of cosine of 22x. And that's an integral we can do and handle pretty quickly. So if I just integrate this, I'm going to get sine of 2022x. I just need to divide by 2022 on this. And we just need to evaluate from 0 to 2 pi. So when you plug 2 pi in here, any multiple of 2 pi inside sine is going to go to 0. And then again, you plug in a 0, you get sine of 0. So this whole piece is actually going to 0. So just this first integral, this 1, I'm going to get rid of that. That's going to 0. And we have this reduced down to 3 integrals now. Okay, sorry, I've rewritten this all with t and y now, and we just have our t and y values down here. So we'll come back and substitute in these values for t and y later, but I just wanted to keep track of what the angle really is. So continuing on with the integral, we have these two right here that are really similar, and let's just look at one of them. So if I multiply in cosine of 22 here to this first one, we're going to have, I'll bring my 2 outside of this integral. We're integrating from 0 to 2 pi, of course, still. And then we're going to have cosine of 2022x. We'll have this sum of k from 1 to 100. And then here we have cosine of kt. But again, t is 100x. Let's just put back in our 100x just so we can try to be clear on what's happening. And now from here, this integral is still kind of tricky because the problem is this is actually a sum of 100 terms. We could break it into 100 different integrals, but we're going to need kind of a shortcut way to deal with this. Well, just notice that each of these, they're going to have the form cosine of a, where a is really 2022x. Cosine b is going to be some multiple of 100x. We can use the different angle formula for cosine for this, and that's just going to be 1/2 times cosine of a minus b plus cosine of a plus b. So then we took our 100 integrals and we broke each of them into 2. So now we have 200 integrals. So we're making it worse. So when we integrate one of these things, we're going to get something like if we were integrating cos AB, we're going to get sine a minus b over a minus b. But when we evaluate that from 0 to 2 pi, we already found that when we plug 2 pi in, we're going to get back 0. We plug 0 in, we're going to get back 0. So for this integral, it's pretty much always going to be 0. Now the only exception we have to look out for is what happens when a minus b equals 0. Okay, because then this is 1, or if a plus b is 0. But we know that a is 2022x, and we know b is going to be this thing, and neither of those are ever negative. So this angle is never going to be 0. So if a plus b is 0, then this is always going to 0. Then similarly, we can look at a minus b and see when is our a minus this b value going to be 0? Well, it's never going to be 0 because 100 doesn't divide into 2022 evenly. So there's no value of k that's going to get us 2022. So this is never going to be 0. And so this piece is always going to 0. So even though this thing here is actually 200 integrals, when we break it all out, they're all going to 0. And so we don't have to worry about that piece. But then we can use almost the exact same logic on this one here as well. Because on this one, the only difference is this y value, which is 102x. So we could just kind of manipulate this a little bit and get it to work with it. So like we can write this. So this b value in this case is going to be jy, which is 102x. And when we do the same thing and break this out with our cosine AB, we end up in a very similar situation. Our a plus b angle, again, of course, is never going to be 0 because both these are positive. But our a minus b, that's also never going to be 0 because again, 102 doesn't divide evenly into 2022. So for all 100 terms here, none of these are going to equal 2022. So a minus b is never 0. So again, this whole integral here, this whole piece is going to 0 for every integral. So that's pretty nice because we've eliminated all this and I've made a total mess of the board, but all we have left to look at really is this last case. So let me clean up the board and we can just focus on this last chunk right here. Okay, now it feels good to have some more space on the board. That was getting kind of messy. So now that we have this down to just one term, what I want to do, I'm going to take this 4 out front of the integral. We don't need to worry about that because it's a constant. So at this point, then I'm going to bring back our t and y values just so we can see what everything is. I think it's nicer to have that in there. So let me put those back and we'll continue. Okay, now it's good news that we kind of have it down to one expression, except for the fact that we have 2 series multiplied together with 100 terms each. So when we multiply these together, every single term is just going to look like cosine A times cosine B. And that's what we saw on the previous board, and we have a formula for that. But then from there, we're going to be multiplying cosine of 22x into each one of these. Let's call 22x, let's call that c. So if we imagine multiplying cosine of c times this, we'll say cosine of c times cosine of a times cosine of b. Then we're going to distribute in a cosine of c into this thing here. But then from here, you notice that each of these, it's actually in the same form as this cosine a times cosine b. So we could just apply this same formula again and get another formula for 3 angles. So applying that different angle formula again, we get this formula down here to the bottom. So this is actually not bad because you can see that even though we've got a lot of terms, what we've done is we've taken this whole integral and just reduced it down into cosines. Of course, now it's going to be a huge list of integrals, but each one is just a cosine integral that we can integrate. And because these are just cosines, they're just going to integrate into sines divided by, some constant value, which is going to be one of these. But what we know from that is each one of these, when we integrate it to sine, it's going to be 0 unless we have zeros in here. The only problem is when these things are going to 0. So what I can do is just take this expression and then we can integrate this, but we're only integrating it when the angles are 0. Okay, so now at this point I've boiled this whole thing down to like potentially 4 integrals. I'm kind of being sloppy here because we don't really know how many of these there are yet because we haven't determined what the zeros are. So I'm just kind of writing it this way to show that like when we have cosines that are 0, we're going to integrate them, but we don't know what's what yet. But one thing I can do here is we can just cancel my 4 with 1/4, so we're not worried about that now. And so let's just be clear about what our A, B, and C is. So C, we said was 2022x. Our A is going to be this, so our A is going to be 100kx, where k is an integer from 1 to 100, and our B is going to be 102jx, again, where j is an integer from 1 to 100. So again, because our indexes are starting at 1, they're always positive. So everything's always positive. So c plus a plus b, this can never be 0. So this term is just not there. I'm just going to cross that off because that's never going to happen. So now with these terms right here, we really have a linear Diophantine equation. I'm not going to really go down the road of how to solve that right now because that would be like a whole nother video. But I think we can get to some values pretty quick. Okay, so rather than getting into too much of the number theory on this, we just need to kind of find the j and k values. They're going to make this work. And what you can find is, because we have a 100 coefficient on the k, we really need this term here to end in 22 or 78 in order to get us to an even multiple of 100. And so what I found for that was there's 4 values of j we can use. There's 11, 39, 61, and 89. But once we have our possible j values, now we just have an equation with one variable. So it's going to be really easy to solve for k. So like just taking the first example for 11, like 11 times 102, this is going to give us 1122. But if you add 900 to this, that's going to be equal to 2022. So then we're saying here that 100k is going to be equal to 900. So our k value is just going to have to be 9. So solving for k for each of these cases, we're going to have 9. For this one, we're going to have 60. For this one, we're going to have 42. And then for this one, we're going to have 111. And then you can just verify for each of these combinations of j and k, plugging into this equation, using either a plus or minus, you can get back to 2022. Now, one thing I notice here is this one doesn't work, right? Because we're only allowed for j and k to be between 1 and 100. This is outside that range, so this is not a good value right here. But each of these other pairs are going to work, and that's going to give us a 0 in this equation. So we're going to have, in each of these cases, we're going to have a cosine of 0 here. So now that we've determined that we have 3 zeros for our angles on cosine, we can finish this off. Okay, so now we've boiled our integral just down to cosine of 0 plus cosine of 0 plus cosine of 0. Of course, like I had mentioned earlier, cosine of 0 is just 1. So now, after all that work, we're just integrating the number 3 from 0 to 2 pi. Well, that's just going to give us 3x evaluated from 0 to 2 pi. Plugging in 0 and 0, plugging in 2 pi, we get our final solution of 6 pi. Okay, wow. That was quite a bit of work. I don't know why this was one of the hardest ones to explain for me. That was just a lot to, I'm gonna have to check the record time. I know I'm gonna edit a lot of this stuff out, but it took me forever to record this. So I hope it made sense. We'll stop it there. Thanks everyone for watching. Have a good day.